Am I audible?
Yeah, good evening, ma'am.
Hello, ma'am. Good evening.
Okay, fine. So here is the link of today's session in the chat box. Okay, so today we are going to revise week 5 to 8. So I hope week 1 to 4 is the easiest part, right?
Yes, ma'am.
So today week 5 to 8 we will revise. Okay. So we'll start with what is null space of a matrix. Okay, so let A be an m by n matrix. So for any m by n matrix, the subspace X in Rn such that Ax is equal to 0. That is a set of all solutions of this homogeneous system. Okay, so this is called the null space of this matrix, a null space of a matrix A. Okay, so just recalling what are homogeneous systems. So this is a homogeneous system Ax equal to 0. So remember, for a homogeneous system, it always has a solution. What is that solution?
0.
Yes. So it always has X is equal to 0. So 0 belongs to this space always. Okay. And if it is a square matrix and the determinant is non-zero, you know that this is the only solution. Okay. Fine. So the same should be the case for the null space of a matrix also. Okay. Fine. Nullity of a matrix is the dimension of the null space of A. Okay. And if you are given a system, given a matrix like this, so you know how to find the null space and null space and nullity of A. How do you do that?
The number of independent variables.
Yeah. So first of all, you have to look at the REF form. So in the REF form, you have to look at the pivot elements. So in the matrix in the REF or RREF form, if the ith column has a leading entry of some row, we call xi to be the dependent variable. And if the ith column does not have the leading entry, we call that variable to be the independent variable. So here you see this column has a leading entry and this column has a leading entry. It means you see that here you are having, is this a
Rank
dependent or independent variable? First one, x1.
Dependent.
Yes, so x1 is dependent and x3 is dependent. So x1 and x2, x3 are dependent variables and x2 is the independent variable. So what is the null space and nullity of A here?
X2 is the null space. So 1.
What does it mean by x2 is the null space?
So 1 is the nullity of this matrix.
What do you mean by 1 is the nullity? How do you say that?
Because that's the independent variable.
X1 and x3, two dependent variables are there, and x2 is the independent variable. Now, how do you find the null space first of all? So your null space definition is Ax is equal to 0. So you should have.
We write x in term of x2, x1.
All right. Yes, ma'am.
So here from this you get that x1 is 0 and x3 is 0, right? So you only have x2 here. So it means what? What is the null space of A? Can you tell now?
0, 1, 0.
Yeah. So you can maybe write it as 0, x2, comma 0, where x2 is in R. Which is same as span of 0, 1, 0. Okay. So now what is the nullity of A? You have only one vector in the basis of the null. So this is a basis now, right? Basis for the null space. So you have only one element in the basis. So nullity is 1, or the other way you can say is that you have one independent variable and that contributes to the nullity. Okay. So this is how you find the null space of a matrix. All right.
Ma'am, can you please zoom in?
Yeah, sure. Okay. Fine. So what is the rank nullity theorem says? Rank nullity theorem says that rank of A plus nullity of A is equal to n. Okay, now you are given a 2 by 2 matrix. So now what should be the rank of this matrix? How do you identify the rank of this matrix? Okay, how are rank and determinant related?
If determinant is
Row
0, then
echelon.
rank
Yeah. So determinant of a matrix A, so since it is a 2 by 2 matrix, determinant of A is non-zero if and only if, let us say, A is an n by n matrix. If and only if rank of A is equal to
N.
n. Okay. So now here, what is the let us call this matrix to be A. What is the determinant of A?
A minus 6.
A minus 6. Okay. So what happens when A minus 6 is non-zero?
A cannot be equal to 6.
So what happens then to the rank?
Rank is n.
Rank of A is
2.
2. So if rank of A is 2, then nullity becomes,
0.
0.
yeah, nullity of A is 0. So then what should be your A so that nullity is equal to 1?
6.
6.
So if A is equal to 6, you know that rank of A is 1 and also nullity of A is also 1. Okay. Fine. Is it possible the rank is equal to 0 in this case?
No, ma'am, because for rank 0, it should have all entries 0.
Yeah, it is a non-zero matrix. Okay. Fine. The nullity of a non-zero scalar matrix of order 3 must be 3. What is a scalar matrix?
A diagonal matrix with entries.
Entries
So
same.
it is of the form A, suppose A is equal to alpha times of I, alpha is in R. So such a matrix is called a scalar matrix. Okay, and here it is given that it is a non-zero scalar matrix. So in option 1, alpha is non-zero and it is a 3 by 3 matrix. So it is basically of this form. And all the other entries are 0. Okay, so alpha is non-zero. And what should be the first, what's the rank of this matrix?
3.
So what should be the nullity?
0.
Ma'am, I think we can infer it by saying that it has no independent variables.
It has no,
Independent variables.
okay, you can say it in any way. Okay.
Okay, ma'am.
Okay. Then next thing is that the nullity of a non-zero diagonal matrix of order 3 must be 3. So you are having a 3 by 3 matrix. So let's say A, B, C. Okay, it is given that your A, B, C, all of them together cannot be 0 because it is a non-zero diagonal matrix. Okay, so the product A, B, C is non-zero, we can say. Okay, so now what can be the nullity of this matrix? What happens when one or two of them are 0? Okay, let us consider the scenario when all of them are non-zero. If all of them are non-zero, so this is the case scenario. If when all of them are non-zero, then what happens?
Nullity will be 0.
0.
Sorry. What's happening? When all of them are 0, then you know that nullity of A is 0. Suppose you have A is 0 or B is 0 or C is 0. Any one is 0, then what happens to the nullity?
Maximum
become 1.
2.
Nullity
Nullity
is
will be
2.
yes.
Nullity is 2 or 1?
1.
1, ma'am.
Nullity is 1, right? Okay.
Yes, no.
Suppose you have two of them to be 0, A, B 0 or A, C 0, or you have B and C to be 0. In that case, what happens to the nullity of A?
2.
2.
Okay. So you know that all of them together cannot be 0. Okay, all of them together cannot be 0 because it is a non-zero diagonal matrix. So you only have these three options. So the nullity of a non-zero diagonal matrix of order 3 can be at most 2.
2.
It cannot be 3. Okay, fine. Let A be a nullity of let nullity of the matrix A be 2. The rank of the matrix A, we have done this already. So what?
Why the
Yeah.
why the nullity of diagonal matrix is 2 at most?
That is what we said. Suppose, see, when will you have the nullity to be 3? When the rank is equal to 0. So rank is 0 when all the entries are 0. But here it is a non-zero diagonal matrix, so all the entries cannot be 0. Right?
Yes,
You
ma'am.
understand?
Right.
You understand?
Yes, ma'am.
Yes.
Okay. Okay. Let nullity of a matrix. Yeah. Is there any question? Okay. For any m by n matrix, what do you know about the rank of A? It should be less than or equal to
Minimum of m, n.
minimum of m comma n. Right? So now here, what is that you can straight away tell about the rank of the matrix?
It will
Rank
be
of A is less
4
than or
minus
equal
3.
to 3. So this is the first observation you have. Now what about the rank nullity theorem? What does it say? Rank
rank
of A
plus nullity is equal to dimension.
plus nullity of A is equal to what?
Number of columns
Dimension.
So here what is the number of columns?
4.
4. So here you have rank plus, this is 4, so rank should be 2. Okay, fine. So which of the following options are correct for a square matrix A of order n by n, where n is any natural number? If the determinant is non-zero, then the nullity of A must be 0. Is that
Yes.
true?
Correct, ma'am.
Yeah, when the determinant is non-zero, you know that rank is
N.
full rank and hence the
Dimension.
nullity is 0. Okay, so this is incorrect. If the nullity of A is non-zero, then the determinant of A must be 0. Is that correct?
Yes, ma'am.
Again, using rank nullity theorem, if nullity of A is non-zero, if nullity of A is non-zero, what happens to the rank of A?
Less than n.
It is strictly less than n. If rank is strictly less than n, you know the determinant of A is equal to 0. And hence option 3 is correct and this is incorrect. Okay. Fine. If A is a 3 by 4 matrix, then which of the following options are true? Already we saw the first option is correct. So if the first option is correct, what about the nullity? Rank is less than or equal to 3. So it means rank can be 0, 1, 2, 3. Right? So these are the possible options for rank. So what is the possible option for nullity? You know the total number of column is 4. So what are the possible options for nullity?
4,
4,
3, 2, 1.
Okay. So nullity must be greater than or equal to 1. It cannot be 0 in this case. Okay. If A has 2 columns which are non-zero and not multiples of each other, while the remaining columns are linear combinations of these 2 columns, then nullity of A is equal to 2. Is that correct?
Yes, ma'am.
So if 2 columns are non-zero, not multiples of each other, it means that your rank is
2.
2.
So if rank is 2, you know that nullity is 2. Okay, so rank of a matrix is equal to number of linearly independent rows or columns. So in this case, from the given information, we know that there are 2 linearly independent columns, hence rank of A is equal to 2. Okay, fine. Okay, so what is a linear transformation? A function t from V to W between 2 vector spaces V and W is said to be a linear transformation if it satisfies these 2 conditions for any vector V1, V2 and any scalar C in R, right? So always we should remember that T of 0 is equal to 0 for any linear transformation. Okay, so you know that every linear transformation is related to a matrix and every matrix is related to a linear transformation. Now here what is given to you, let T from R2 to R2 be a linear transformation such that T of 2 comma 1 is equal to 3 comma 2 and T of 1 comma 3 is equal to 0 comma 0. So what is the first observation you have to do is that what are these two vectors here? Let us call this to be V1 and V2. Okay, so now consider this vector V1 and V2. Are they linearly independent? Are they linearly independent?
Yes, ma'am.
Yes,
There.
ma'am.
So if they are linearly independent, will they form a basis for R2?
Yes, ma'am.
Yes, ma'am.
So it is forming a basis for R2, right? So if it is forming a basis for R2, then you know that you have the images of the basis. Now take any vector V, which is x comma y. How do you express it as a linear combination of V1 and V2? So here it is 2 comma 1 and here 1 comma 3. So what are alpha 1 and alpha 2 for x comma y? So 2 alpha 1 plus alpha 2 comma alpha 1 plus 3 alpha 2. So what are your alpha 1 and alpha 2 in terms of your x and y? How do you do that? You have to solve the system of equations, right? So if you solve them, what will you get? So let us call this equation 1, equation 2. So equation 1 and 2 times of minus 2, let us say. So 2 alpha 1 plus alpha 2 is equal to x minus 2 alpha 1 minus 6 alpha 2 is equal to minus 2y. So what do you have? Minus 5 alpha 2 is equal to x minus 2y. So alpha 2 is equal to 1 by 5 times or minus 1 by 5 times of x minus 2y. So what should be your alpha 1 then? So let us substitute it here. 2 alpha 1 is equal to, there is some problem with the software or pen, I don't know. Sorry. 2 alpha 1 is equal to
1 by 5 x minus 2y.
x minus or x plus 1
Plus-
by 5 times of x minus 2y. So you have 6x by 5 minus 2y minus 2 by 5y. Is that correct?
Yes, ma'am.
So 1 by 5 times of 6x minus 2y. Okay. So this is 2 times of alpha 1. So alpha 1 should be 1 by 10 times of this. So you can simplify this and see that alpha 1 is equal to 1 by 5 times of 3x minus y. Okay. So here you see that which one of these options will coincide. So what is your T of x comma y now? T of x comma y is alpha 1 times of T of 2 comma 1 plus alpha 2 times of T of 1 comma 3. And what is T of 1 comma 3? It is a 0 vector and T of 2 comma 1 is 3 comma 2. So you have 1 by 5 times 3x minus y into, this is 3 comma 2, right? What was it? Yeah, it is 3 comma 2. So you have 6x minus 3y, sorry, 9x minus 3y, comma 6x minus 2y, 1 by 5 times of this. So is there any option coinciding with this? 9x minus 3y, 6x minus 2y. So option 3. Okay. So what are the steps we have done here? So you see, whatever is the basis given to you. Suppose you are how steps to obtain a linear transformation of the images of the basis of V under T is given. Okay. Suppose the given basis of Rn is this. Okay. Take any random vector V is equal to x1, x2, xn in V and write V as a linear combination of this. Find the coefficients of alpha I in terms of x1, x2, xn by solving system of linear equations. Then apply T on both sides and substitute the values of T, Vi and alpha I. By simplifying, we get the expression for T. This is the general procedure. Whatever we have done in the previous example, I have written it as a general procedure for finding T given this information. Is this clear for everyone? Okay. Fine. A linear transformation. Now, so the next we are going to see 1-1 onto and bijective transformations. So a linear transformation which is 1-to-1, it is a monomorphism. So the definition is TV1 equal to TV2 implies V1 equal to V2 or TV equal to 0 implies V is equal to 0. This is for 1-to-1. And for onto or epimorphism, you call that, so you call it to be onto if for every element in the codomain there exists a pre-image for that element in the domain. Okay. So for every W in capital W, you have a vector which is the pre-image of W. So if both 1-to-1 and onto, it is called an isomorphism. Okay. Fine. So we define two vector spaces V and W are isomorphic to each other if and only if there exists an isomorphism T from V to W. So important fact is that any n-dimensional vector space is isomorphic to Rn. So what does this give you? Suppose you have T from V to W is an isomorphism. Okay. So the first thing you should know is that dimension of V is equal to dimension of W. This is an if and only if condition. What does it mean? Suppose there are two vector spaces of the same dimension, then also you can find an isomorphism. Okay. So it means there exists, let me write in bracket. So if there are two vector spaces of same dimension, then there exists a transformation T from V to W, which is an isomorphism. And also whenever you have an isomorphism between two vector spaces, then the dimension should be same. Okay, so this is an important fact about isomorphism. All right. Okay. Now suppose you are having, let me give you some example. So let us say V1 is equal to so what is dimension of V1? Can you say?
2.
Dimension of V1 is 2 because this reduces to 2y, y, z in R3. Right? So it means you have only two variables here, unknown variables. Dimension is 2. Right? So if the dimension is 2, to which space is it isomorphic to? Can you tell?
R2.
R2. Okay. So can you give an example of a matrix space which is isomorphic to V1? An example from a 3x3 case and from a 2x2 case, both can you tell?
Ma'am, diagonal matrix.
Okay, so here we can make the diagonals to be 0. All right. Okay. Any other example, any other 3x3 matrix? So what can you say in that case? Suppose you want to consider a 3x3 matrix. Again, let's take a diagonal matrix itself. What is the additional condition you need so that the dimension is 2?
C equal to 2a plus b, you can say.
Yeah, you can say that also. This is fine. Okay. So you see that all of these are having dimensions, dimension 2. So all of these are isomorphic vector spaces. Okay. Fine. So now moving to week 6 topics. So we already know that null space is a subspace of V and range space is also a subspace of V, and the dimensions are nullity and rank, right? So relation between injective map and nullity. What is the relation? T is an injective linear transformation if and only if kernel T is equal to 0. Okay, so if the nullity is 0, then only you can have an injective linear transformation, because the definition says that TV is equal to 0 implies V is equal to 0. This is the definition of T is 1 to 1, right? So it means what? Whenever you have this condition, the only solution you have is the 0 solution. It means 0 is the only element in the null space. Okay, and conversely, if 0 is the only element in the null space, then TV equal to 0 will imply V equal to 0. So you should remember this important fact about the relation between injective map and nullity. Same way, what is the relation between surjective map and rank? So the definition of surjective map, if you remember, T is onto means, so for every W in W, there exists V in V such that T V equal to W, right? It means what? Your range of T is the whole of W. If range of T is whole of W, then what is rank of T?
Dimension of W.
Dimension of W. Okay, so rank of T is dimension of W, and the range is both are having the same dimensions. So you see that here range of T is equal to W, so rank of T is equal to dimension of W. So now using rank nullity theorem, what can you say? Rank of T plus nullity of T is equal to, here what is that you have in rank nullity theorem?
Dimension of V.
Dimension of W.
Dimension of W or V?
B, ma'am.
V, ma'am.
Dimension of V. Okay, and here you are having dimension of W plus nullity of T is equal to dimension of V. Okay, now if nullity of T is also 0, this also combined here, then this becomes 0. So this is the case when T is an isomorphism, then you know that rank of T is dimension. I'm combining both now. So you see that here nullity is 0 and here rank of T is dimension of W. So you see that when you have both injection and surjection, you end up with dimension of V is equal to dimension of W. Okay, fine. Okay, so just using the information given above, you can answer this question. T is a one-to-one linear transformation if and only if there does not exist any V in non-zero such that TV equal to 0. Is that true? So
Yes, ma'am, it is true.
So it is same as saying TV equal to 0 implies V is 0. Right? So this is correct. So T from R2 to R2 is a surjective linear transformation. Then it cannot be injective.
False, ma'am.
Okay. So here you know that for you take any transformation T of X is equal to AX, where A is a matrix ABCD with the determinant of A non-zero. Then what can you say about T? T is both one-to-one and
1 to 1 and
On.
R 2.
1, 2.
okay. So here you see that it is given that if it is surjective, it cannot be injective, but definitely that is not the case. It is possible that such a transformation can be both one-to-one and onto. But is it possible the other way around? That it is only one-to-one but not onto.
No, ma'am, it is not possible.
Okay. So this is another thing. Suppose you have T from Rn to Rn, then T is one-to-one if and only if T is onto. Okay. Remember, this also is an important fact. So this is incorrect. If T from R to R is a linear transformation which is not injective, it means what? TV is equal to 0 does not imply V is equal to 0. So it means what? There are many other values for which you have TV equal to 0. So for example, let us say V is some element in R minus 0 and TV is equal to 0. Since R, so you can say that V is a non-zero element. So what is span of V, can you tell?
That is entire R.
Yes, span of V is entire R. So it means V is a basis element. If the basis element is mapped to 0, what happens to the entire transformation?
Maps to 0.
Yes. If the basis element is mapped to 0, then the entire transformation will be mapped to 0. So then T must be 0 is the correct statement. Is this clear? Option 3.
Yes, ma'am.
Okay. So what is option 4? If there exists some non-zero vector V in V such that TV equal to 0 for a linear transformation T from V to W. So what does it mean? So
It
what
is
does this
not on-
condition mean? Your null space of V is a non-zero vector and it belongs to your kernel. So it means T is not
1-to-1.
1-to-1. If it is not 1-to-1, it cannot be an isomorphism, which is correct. Okay, clear? So just from the basic understanding of 1-to-1 and onto mapping, these conditions are given. Okay. Okay. So suppose you
So
are.
kernel corresponds to 1-to-1 and image corresponds to 1-to. Is it true?
Can you please repeat your statement?
So kernel mapping, that is case of 1-to-1, and image mapping, it is the case of 1-to. Is it true?
See, the property of kernel is related to 1-to-1. Kernel being singleton 0 is related to 1-to-1 property. And image equal to dimension relates to onto property. Okay?
Yes,
Fine.
ma'am.
Okay. So one more thing I'll ask here, just maybe reframing this statement given here. Suppose you have T from V to W and T is both 1-to-1 and onto. What can you say about the matrix representation of T?
The determinant is non-zero.
Yeah. So you should know that determinant of A is non-zero. It means A inverse exists. Okay. So the converse is also true. Okay. Remember this. So the rank nullity theorem says that rank of T plus nullity of T is the dimension of V. So if T is injective, rank of T is equal to dimension of V because nullity becomes 0. And if T is an isomorphism, dimension of V and dimension of V are same. Okay, fine. And also here one more thing. If T is onto, then what? Rank of T is equal to what?
Dimension of W.
Yeah. So combining these two, T is 1-to-1 and onto together will give dimension V is equal to dimension W. All right. Okay. So matrix representation, you know how to do this. So let us directly go to a problem. So if T from R3 to R3 is a linear transformation defined as follows. So this can be represented as TV is equal to AV. So any linear transformation, you can represent it in this way, TV equal to AV. Remember this, I have told you several times. Any linear transformation can be written in this format and anything defined in this way will represent a linear transformation. It is true in both the ways. Okay. So here you are having TV equal to AV where your matrix A is given here. Okay. And your V is XYZ. Okay. So which of the following options are true? T is injective if and only if the system of linear equation AV equal to 0 has a unique solution. Is this true?
Yes,
ma'am.
ma'am.
Okay. So if AV is equal to 0 has a unique solution, what does it mean?
That means T is a isomorphism.
No. First of all, what is the null space of A?
0 only.
0.
Okay. So you can say T is an isomorphism that is there, but you have to be careful about this domain and codomain. Here both are same, so you can say that, but straight away don't jump to that statement. Okay. Be careful. So null space of A is equal to 0. If null space of A equal to 0, you know that T is injective. Okay. So this option is fine. T is injective if and only if rank of A is 3. Is that correct?
Yes, ma'am.
True.
Yes.
So because rank of A will be 3 only when your null space is
0.
0.
all right. If the system of linear equation AB equal to B for any B in R3 has a solution, then T must be surjective.
Yes, ma'am, it is correct.
Right? So it means what? For every element in the codomain, you have a image, pre-image. Okay. So that is what is meant by having a solution to this homogeneous system for every B in R3. Okay. So this is true.
Ma'am, what is the pre-image again?
What is a pre-image? Suppose you have T of V is equal to W. W is an image of V. And V is an pre-image of
W.
W. Both are under T.
Yes, ma'am.
Okay. Okay. So if T is not surjective, then there exists some B in R3 such that the system of linear equation AB equal to B has no solution. Is that true?
Yes, ma'am.
It's not surjective. Okay. So from this, what do you observe? So if you are having transformation T from Rn to Rn, and you have the corresponding matrix representation, what can you tell about the homogeneous system and the non-homogeneous system? What can you tell? So from here, so the homogeneous system will have a unique solution when T is 1 to 1. Okay. And the non-homogeneous system will always have a solution for any B if T is on 2. Okay. So these facts are given as a question here. So these are important facts to remember. So I hope you all understand how it happens here. Is that clear?
Yes,
Okay.
ma'am. Ma'am,
Okay.
if Ax equal to B has no solution, then linear transformation cannot be possible, right?
Linear transformation is possible. It is just that it is not on 2.
If it has no solution, right?
It is, if it has no solution, it is possible that it is still a linear transformation. It has no, it is just not on 2.
Okay.
So for example, if you let us take T from R2 to R2, a very simple example I will give. T of x comma y is equal to x comma 0. Is 1 comma 1 there in the range of T?
No, ma'am.
It is not there, right? So is it still a linear transformation?
Yes, yes.
So you see that for Ax is equal to B, where B is this vector, there is no solution. A is the matrix representation of T. Is this
Okay,
clear?
okay, ma'am. Okay.
Okay. Okay, now look at this question, everyone. What is the matrix? First of all, what should be the order of the matrix representation? T is from R3 to R2. So what should be the order of the matrix representation? So for any T from
So
Rn
2
to
cross
Rn,
3.
2 cross 3.
matrix should be M by N.
Cross N. Yes.
Yeah. So here, what should be the order of the matrix?
2 cross 3.
Yeah. So without even checking, you can say that this is incorrect because this is a 3 by 2 matrix. So this is incorrect, you can say. And this one, you have to make sure it is correct. So what? You just look at what is T of 1, 0, 0. What is the answer?
2, 0.
2, 0. And what is T of 0, 1, 0?
1, 0.
And T of 0, 0, 1?
0, 1.
Okay. So these forms, so this is your T1, T2, T3. Okay. So you see the option 2 is correct. So what is the basis for the null space of T? So your T is here. So you have 2, 1, 0, 0, 0, 1. It is already in the REF form. So now can you tell what are the independent and dependent variables?
Ma'am, it's not in REF form. You need to make, you need to divide
Okay,
it to.
Yeah. Divided by 2 is needed. But anyway, here we can straight away calculate it. Yeah, that is correct. It is not in our REF. Okay. Now, anyway, so if you solve this, what will you get? 2x1,
x3
X1
equal to
is
0.
0 and x3 is equal to 0.
right? So you have
X3 is the
equal to
independent
0
variable.
and x2 is equal to minus 2 times of x1. So it means your null space of A is equal to x1 minus 2x1 comma 0, right? x1 in R. So it is the span of which vector, can you tell?
1 minus 2 0.
1 minus 2.
Okay. So in place of 1 minus 2 0, if it is given as, let us say, 2 or minus 2 4 0, is this correct answer? Is this answer correct?
Yes, ma'am, it is
Yes,
correct.
ma'am.
Okay. In fact, if you consider this as V, then any KV where K is a scalar should be a null basis for the null space. Do you agree with me?
Ma'am.
Okay.
Yes, ma'am.
Yes, ma'am.
Okay. So this is definitely incorrect. There are two elements in the basis. So a basis for the range of T is this or this. But before even looking at this, what is the rank of T here? Just by looking at the matrix, you can say that rank of T is
2.
2.
rank of A is equal to rank of T is 2. So if rank of T is 2, then you know that the basis of the range should have 2 entries. So
elements.
this option is incorrect, but we have to verify whether this option is correct. So you see that 2, 1 and 0, 1, does it form a basis for R2? So your codomain is R2. So
Yes, ma'am, it is forming.
yeah, so you see that here, in this case, the basis of for the range can be any two linearly independent vectors from R2. So this is correct only. Okay.
Ma'am,
Yeah.
can you differentiate between null space and kernel space of T?
Both are same.
Both are same, right? Then
Yeah.
why we are getting some different basis with respect to some particular ordered basis for the linear transformation?
Sorry, when are we getting different answers?
Yeah. I'm saying that if other than standard ordered basis,
Mm.
I mean, with respect to those ordered basis for a linear transformation.
Okay, bases can be different. Yeah, I understand what is your question. Suppose you are having two different matrix representation with different with respect to different bases, right?
Yes, ma'am.
So in that case, you have two different null spaces, correct?
Yes,
But
ma'am.
nullity is still the same, correct?
Nullity
That is
is same.
always possible. That is always possible. Null spaces can be different depending on the matrix representation, but nullity will always be the same. Okay, that is
Okay.
possible.
Okay.
It is just because of the representation we are considering. Okay.
Okay, ma'am. Ma'am, can you use that method? I mean, I'm not able to use that. How to find the how to find a basis for the kernel space of a linear transformation with respect to some other ordered basis, which is not standard ordered.
So you just have to find the matrix with respect to that basis and find the null space of the matrix. That's all.
After finding the null space, we need to do some multiplication with the standard ordered basis which we have
No,
considered,
that
right?
is not required. See, let us say that suppose you are having that V1 and V2 is a basis for R2. Okay, and this is not a standard ordered basis. So now you need to know what is the matrix representation with respect to V1 and V2. Okay.
Okay.
Okay. So here you have alpha 1, alpha 2, alpha 3, alpha 4. This is your matrix representation. Find the null space of this matrix that will give you the null space of the transformation.
Will that give the kernel space? I mean, the basis. I mean, from that, can we find a basis for the kernel space of T?
Yes, definitely you can find.
Okay, the basis which we have found as the null space of T, that is same as the kernel space of T,
Yes.
right?
Yes.
Okay, ma'am. Okay, ma'am. Thank you.
Okay. Okay. So let T from R2 to
Ma'am,
R2.
excuse me.
Yeah.
Ma'am, in previous question, in option number 3, option number 4 for ma'am, x2 is dependent from the matrix. The dependent is x1 to yeah, and x2 is equal to minus x1. Then here x1 is independent. Whatever we want, we can put the value x1.
Yes, you can put any value for x1.
Yes, ma'am. But from the matrix, the our pivot is row one element of the row one. That is dependent x1 from A.
Yeah, here your x2 is dependent on x1. X2 is the dependent variable here, right?
No, ma'am. From the matrix, if we convert it in row reduced form, then
So you see, you will have a pivot element here and you will have a pivot element in the third column, right?
yes, ma'am.
So if you are having a pivot element here and pivot element here, so which is the dependent variable and which is the independent variable?
X2 is dependent. Okay.
X2 is independent.
And x1 and x2, x3 is
And
dependent.
dependent. So in that case, if you want to consider it in this way, it does not matter. Your answer is still the same. In that case, if you want to write it properly according to this definition, so you can write it as x1 is equal to minus 1 by 2 x2. That's all. It's not going to change anything. Okay?
Okay.
All right.
Madam, in this question, how this option 5 is correct?
Option 5, how it is correct? So here you see that what is your rank of t? Rank of
2.
is 2.
2.
Rank of t is equal to 2. What is your range of t? What is your range of t then? If it is full rank, the range should be
2.
equal to the coefficient, right? So any basis of R2 will be a basis of range, correct?
Yeah.
Okay. Okay. Let T from R2 to R2 be a linear transformation such that T of x comma y equal to x comma 0 is T 1 to 1 and onto or onto. So according to the definition, so T is 1 to 1. If TV equal to 0 implies V is equal to 0. So here what happens? T of x comma y is equal to x comma 0. Let us assume it to be 0. So what is that you get?
Ma'am, all the elements on y-axis is mapped to 0.
So here you don't say that. So you say that, yeah. So the null space is all the elements in the elements in the y-axis. That is what you are saying, right?
Yes, ma'am.
Okay. So here you have x is equal to 0. So your null space is span of 0, 1. So it means you see that there exists V non-zero. For example, you can take 0, 1 or 1, 1 such that TV is equal to 0. What happens to this T of 0, 1?
0, 0.
So it means T is not 1 to 1. So now without even verifying onto, can you tell whether T is onto or not?
Yes, ma'am. T is not isomorphic, so it is not onto.
T is not 1 to 1, so it is not onto. Okay. So since the domain and codomain are same, you know that T should be 1 to 1 if and only if T is onto. So here T is not 1 to 1, so it cannot be onto as well. So how do you prove that T is not onto? You just have to show that there is an element in R2 which is not in the range. How do you do that? What is the element you can choose? What is the element?
Ma'am, you can choose 1, 1.
Okay, 1, 1 is not there in the image of T. So it means T is not onto. So this is the direct way of using the definition. How do you use matrix to say prove this? What is the matrix representation of this? What is TE1? TE1 is 1, 0. And what is TE2?
0, 1.
0, 1. Are you sure? What is TE2?
0, 0.
That is 0, 0.
So it means you are getting 1, 0, 0, 0. So this is your matrix representation. And what is determinant of A?
0.
So from this you can say, or straight away also you can say that rank of A is not equal to 2. Or from straight away here you can easily see that rank of A is equal to 1. Right? If rank of A is equal to 1, you know that nullity is not 0.
Yes, ma'am.
So from here you can say that T is not on to, and from here you can say that T is not 1 to 1. Okay, do you understand how I used matrix method to say about 1 to 1 and on to? Is this clear?
Ma'am, can you explain how you got TB is not equal to 1 to 1 direct method?
In direct method, okay?
Yes, ma'am.
On to.
Yes, ma'am.
See, for on to, what is the condition you need? Image of T should be equal to the entire R2. But here it is not the case. I have taken an element from R2 which is not in image of T. So here I missed this, not in image of T. 1, 1 is not there in the image of T. So it is not, image of T is not equal to R2. Okay?
Yes, ma'am.
Okay. Okay, is the direct method and matrix method both are clear for everyone? Okay. So usually for transformations with same dimensions of domain and codomain, matrix method is always convenient. Okay. Okay. Let T from R2 to R2 be a linear transformation that such that T of x comma y is equal to is given by this transformation. Now, how do you verify 1 to 1 and on to? What is TE1? What is TE1?
1, comma 1.
TE1 is 1, comma 1 and TE2 is?
1, comma minus 1.
So your matrix A is equal to?
1 minus 1, 1, 1. Row wise.
Okay. 1, 1, 1 minus 1. TE1, TE2, right? Okay. So now what is the determinant of A?
Non-zero.
Yeah, minus 1, minus 1, minus 2, which is non-zero. It means rank of A is equal to?
2.
2. If rank of A is equal to 2, you know that T is 1 to 1 and on to. Okay, first of all, determinant non-zero itself will tell you that T is 1 to 1 and on. Is this clear? How we did this?
Yes, ma'am.
Okay. Consider a map T from R2 to R2 defined as TV is equal to AV, where V is XY and A is ABCD. Which of the following options are correct? T is a linear transformation. Is that correct?
Yes, ma'am.
Okay. T is both 1 to 1 and on to. You need a condition here. If?
Yes, ma'am. If AD minus BC not equal to 0.
Yeah. So AD minus BC not equal to 0. So this we cannot say. T is neither 1 to 1 nor on to, that also we cannot say. T is 1 to 1 but not on to. Is it possible? This
No,
is
it
also
is
not
not possible.
Not possible, ma'am. Either both or no one.
Yeah. But in this case,
Uh,
we don't have any specific conditions here. So if it is given T maybe, then it is true.
Yes, ma'am.
Okay, here it is given T is, so we cannot say whether it is correct or not. So it is incorrect one. Okay, so the next option here is that which of the following linear transformation is an isomorphism between the vector spaces? First of all, will there be an isomorphism between these two spaces? How will you verify?
By checking the dimension.
Yes, so what is the dimension of V here? So V is Y minus Z, Y and Z. And what is W? X, X and Z. Okay, so here both are having how many unknown variables?
2.
Yeah. So dimension of V is equal to dimension of W is equal to 2. Okay. So first of all, there exists a linear isomorphism. So this option is incorrect. Okay. Fine. So now remember, for an isomorphism, if T from V to W is an isomorphism, what do you know about the range of T or the image of T? It should be equal to?
Same.
Same, ma'am. The dimension of the V equal to the dimension of W.
Image of T should be equal to W. This is what you know about the image. So you have to look at the transformation whose image is equal to W. So out of this three, let us consider the first one. The first one is y comma y comma 0. So in this case, is the image equal to the space W?
No, ma'am.
Because here the elements for which the third coordinate is non-zero is missing. So this option is incorrect. What about the option 2? First two entries are same and third element is any z. So is this option correct?
Yes, ma'am.
Okay. And the third option here you are considering the identity transformation, which is definitely not the case. It will not be having x is equal to 1. Incorrect. Okay. So option 2 is fine. Okay. So if the matrix corresponding to a linear transformation T from R2 to R2 with respect to standard basis for both domain and codomain is given, how do you find the corresponding transformation? So given a matrix, how to find the transformation? Yeah.
Ma'am, you can find T of 1 comma 0 and T of 0 comma 1.
Here matrix is given.
We should find the vectors where the answer will be corresponding to the.
Ma'am, you need to find T of 1 comma 0, which is 2 into 1 comma 0 plus 1 into 0 comma 1, right?
So T of 1 comma 0, you know that it is equal to 2 comma 1.
Yes.
And T of 0 comma 1, you know it is equal to 3 comma 4.
Yes.
So T of x comma y is equal to, you know that x times of TE1 plus y times of TE2, right? Because
Yes,
x comma y is simply xe1 plus ye2. So applying T on both sides, you get this. So x times of 2, 1 plus y times of 3, 4. So 2x plus 3y, x plus 4y. So or since it is only in the standard ordered basis case, you can do this. T of xy is straight away only for the standard ordered basis. You can straight away do this. 2x plus 3y, x plus 4y. Okay. Fine.
Okay.
Remember, this is only when you have the standard ordered basis. So which option is correct? 2x plus 3y, x plus 4y. This one. Okay. Fine. So is this mapping T 1 to 1 and 1 to?
Yes,
What is the
ma'am.
determinant of the matrix? Non-zero. So it is both 1 to 1 and 1 to. What will be the matrix of T with respect to basis beta for W and gamma for R2? What is W here? Maybe for domain, they mean domain and codomain. Okay. So let us do this. How do you do this? How do you do this? Let us say that this is your beta. So what is T of 1, 0?
1 comma 1.
Are you sure
That will
T of
be
1, 0 is
ma'am,
1 comma 1?
that will be 2 into 1 comma 1
It is
plus
2 comma 1. Already we have that information here. It is 2
Okay.
comma 1. You just have to find the coefficients here in terms of 1 comma 1 and 1 comma minus 1. Same way, what is T of 0, 1?
3
It is
comma
3
4.
comma 4, and you need to express it as a linear combination of 1 comma 1 and 1 comma minus 1. So it means what is the equation you need to solve? Alpha 1 plus alpha 2 is equal to 2. Alpha 1 minus alpha 2 is equal to 1. Same way, alpha 3 plus alpha 4 is equal to 3 and alpha 3 minus alpha 4 equal to 4. So if you solve these two equations, then the matrix representation you have is alpha 1, alpha 2, alpha 3, alpha 4 is your matrix representation. Solving the system of linear equation, can I leave it to you?
Yes, ma'am. Sure.
Okay. Fine. Consider the following linear transformation T from R3 to R2 defined by T of x comma y comma z as 2x plus 3z 4y plus z. Find the null space of T. So how do you find the null space?
From
First,
the
we have to
matrix,
find the matrix of
So if you
matrix.
consider the standard ordered basis,
Ma'am,
then can you consider any other ordered basis?
other ordered basis, it is going to take time. Standard basis is the easiest way. So it's always, we go by the easier technique, right? Not by the difficult
hello.
one.
Okay.
What is happening? Think some issues going on. What is this? Sorry. Just give me a minute. Sorry for this, Aisha. I don't know what happened. Let us continue. Are you able to see the screen? Is everything fine?
Yes,
Yes,
ma'am.
ma'am.
Okay, fine. So T of 100. What is T of 100?
2, 0.
2, 0.
2, 0.
0. And T of 010?
0, 4.
0 and 1. And T of 001?
Ma'am, that should be 0, 4,
3,
right?
1. Right?
T of 010.
010 is 0 and 4. Yeah.
4.
Thank you. So T of 001 is 3 and 1. Okay. So what is the matrix you have? T1, T2, T3. So you have 2, 0, 0, 4 and 3, 1. What is the rank of A here?
2,
Rank of A is 2. So what should be the nullity?
1.
So plus nullity should give you the number of columns, which is 3. So nullity should be equal to 1. Okay. So how do you find the null space here? Either you have to do with the REF form or straight away also you can do. So you have 2x1 plus 3x3 equal to 0 and 4x2 plus x3 is equal to 0. So it means what? x3 is equal to minus 4 x2 and x3 is equal to minus 2 by 3 x1. Correct? So what is your null space? Set of all x1 minus 2 by 3 x1 comma minus 4. Sorry, here I want to express x2 and x3 in terms of x. Just the other way around. So x3 x1 is equal to minus 3 by 2 x3 and x2 is minus 1 by 4 x3. So you have minus 3 by 2 x3 minus 1 by 4 x3 comma x3. So if you want to write it without fractions, also maybe leaving out the negative signs, what is that you will get? Can you give a basis element?
Minus 6x3 comma minus
6
x3
comma
6 3
1
minus
comma 1.
minus 1.
1
Maybe
comma 4.
multiplying by 4 is easier, right? Multiplying by 4 throughout, minus 4 maybe, minus 4 if I'm multiplying throughout. So you get 6,
It's 6,
1,
1 and 4.
4, minus 4.
Minus 4, yes.
Okay. So this is a null space of T. What will be the dimension of the subspace image of T?
2.
So this is for A. Here we have done. So for C, choose the correct option. Which is the correct option? T is an isomorphism. Can this be an isomorphism? What is the range and domain and codomain? They are different. Can this be an isomorphism?
No, ma'am.
It cannot be an isomorphism. Is T 1 to 1?
No.
It is not 1 to 1. Is T on to?
Yes, ma'am, it is on 2.
Yes.
It is on to, right?
Yes.
So here you see that rank is 2. So you see that image of T is equal to your codomain. So T is on 2. This is incorrect. Is this problem clear for everyone?
Ma'am, can you explain the third
Yes,
question
ma'am.
again?
Yes,
Which
ma'am.
one?
Yes.
The third option.
Ma'am,
Third solution.
This one, T is on 2.
Yes, ma'am.
See, here what is mean by on 2? If your image of T is equal to the entire codomain, then it means T is on 2. Here rank is 2. What is mean by rank? Rank is nothing but the
Number
dimension
of
of your
independent
image of T or the range of T. Both are same. So if your dimension of image of T is equal to 2 and also image of T is a subspace of R2, that you know, and they are having same dimension, it means they are same, right?
Yes, ma'am.
Okay, fine. Okay. Okay, so the next question here, let M be the set of all skew symmetric matrices of order 3. So what does mean by skew symmetric matrix first of all?
A should
Transpose of
be
A is
equal
equal to the
to
negative
A
of
transpose
minus
equal
A
to A
transpose.
minus of A.
Minus A
A transpose
transpose.
is equal to minus A.
minus A.
Minus of A.
Okay.
Minus of A.
Yeah, so this forms a vector space under matrix multiplication and scalar multiplication. Let T be a linear transformation from M to R defined in this way. T of A is equal to C times of trace of A. What is the nullity of T? Okay. Okay. So first of all, what is that you know about that? What is mean by trace? You already know. It is the sum of diagonal entries of A. So we should know what are the diagonal entries of A for a skew symmetric matrix. By now you should already know the diagonals. What are the
It's
diagonals?
0.
All of them are 0. Why is that so? Because you have AJI is equal to minus AIJ. Right? So you have A transpose. So this is there for any AIJ. In general, when I is equal to J, that is for diagonal entries, AII is equal to minus AII. It means AII is equal to 0. Okay. So for a skew symmetric matrix, we always know that the diagonal entries are 0.
And determinant of A is also 0.
Yeah. So here you see that the diagonal entries are 0. It means the trace of A is 0. Okay. So if the trace of A is 0, what can you say about this nullity of T? So your transformation is a 0 transformation.
The transformation of A is equal to 0.
Yeah. So what is the nullity of T then? All the elements in this space are going to 0. So what is the dimension of this space?
3.
The dimension of the space is 3. Are you sure?
Not defined.
Not defined. The dimension of any finite vector space, so any vector space is defined, right? So here, in fact, it is finite dimensional. So what is the dimension of this space? You know
0,
how
well,
to find the dimension? So any matrix here in M should be of the form A0, A, B, C. Here it is minus A, 0, minus B, minus C, 0.
That's
So what is the dimension
3.
of collection of all such matrices?
3, ma'am.
3, right? So what is the
it's 3
nullity?
for the
It is
0.
3 or 0? It is just 3, right? So your dimension of M is 3. Okay, your dimension of M is 3. So you have here nullity is 3. Is this clear?
Can you explain it again, ma'am?
See here what happens. What is your domain and codomain for T? T is from M to R. Correct? T is from
Yes.
M to R. So now you are saying that your T is 0. It means all the elements here are mapped to 0. Right? What is your null space? Definition of null space. Null space of T is the collection of A in M such that T of A is equal to 0. In this case, it is the entire M. Right? Because for every A, T of A is 0. So null space of T should have the same dimension as M, right? Yes,
Yes,
or no?
ma'am.
Got it?
Yes, ma'am.
Yes, ma'am.
Okay. Okay, so what's the next question? Consider a linear transformation T from R3 to R3 defined as T of x comma y comma z is equal to ax plus ay, z minus bx, y plus cz such that the product is not equal to 0. Product of ABC is not equal to 1. Okay, so which of the following options are true about T? So what is the matrix representation? What is TE1?
1, A, and
1,
0.
comma minus B, comma 0.
0. And what is TE2?
A, comma 0, comma 1.
And what is TE3?
0, comma 1, comma C.
So 1 minus B 0 and A 0 1 0 1 C. Right? So you see option 2 is correct. Option 1 is incorrect. So a basis for the range of T is 1 0 0 0 1 0 0 1 0. 0 here there is a mistake. It should be 0 0 1. 0 0 1. Okay. So how do we see this? So what is the determinant of this matrix here? What is determinant of, let us call this A. What is determinant of A? 1 times of, this
Minus
is 0,
1.
minus 1, minus A times of minus BC plus 0. So it is minus 1 plus ABC. Is that correct?
Yes, ma'am. It is non-zero.
Yes, ma'am.
And it is given to be non-zero.
Not
So
equal to 0.
yeah, so if determinant of A is non-zero, what do you know about the range of T?
That is R3.
So does this form a basis for the range of T?
Yes, ma'am.
Okay, fine. So this is incorrect. This is incorrect. Rank of T is 3. Is this correct?
Yes,
Yes,
ma'am.
ma'am.
So if rank is 3, nullity should be 0.
0.
Is this clear for everyone? Yeah?
Yes,
Yes,
ma'am.
ma'am.
Okay. So moving to week 7 topics. So in week 7, you have first equivalence matrix and similar matrix. So for equivalence matrix, the condition is B is equal to QAP for some Q and P. Invertible Q and P. All right. Okay. So now you know that this is an equivalence relation. So it means it is reflexive, symmetric, and transitive. Okay. So how to find this P and Q? Again, I will not go through these steps. It is already explained to you in the lecture sessions. Please go there if you want to know how it works. I'll go to the characterization straight away. Two matrices A and B are equivalent if A can be transformed into B by a combination of elementary row and column operations. Okay, so if one matrix can be transformed into B by a combination of elementary row and column operation, then A and B are equivalent. So you know that elementary row operations does not change the rank. So two matrices A and B are equivalent if rank of A is equal to rank of B. So this is the easiest way you can determine whether two matrices are equivalent or not. So now given these two matrices, are they equivalent or not? What is rank of A and what is rank of B?
2.
Rank of A as well as rank of B, both of them are 2. So A and B are equivalent. All right. What about these two matrices? Do you need to check anything or straight away can we give an answer? They are
So they are not equivalent.
They are not
They're
equivalent.
not equivalent, so they
because
can't
of not
behave with
same
orders.
orders.
Yeah. Okay. Fine. So for similar matrices, you should have an invertible matrix such that B is equal to P inverse AP. Okay. And remember, similar matrices, you apply this concept only for square matrices. Okay. So verify that similarity defines an equivalence relation between square matrices of the same order. So this we have already verified. So if two matrices are similar, they satisfy equivalent condition. They are equivalent. So it means what? B is equal to QAP, where Q is just P inverse. That's all there. Okay. What is the converse? If two matrices are equivalent, are they similar?
No, ma'am. They
No.
need not be similar.
Yes. So here you have an example. So rank of A and rank of B, what are they?
2.
2. But this is the case I always tell you. A is the identity matrix and B is some other matrix. An identity matrix cannot be similar to any other matrix, right? Because
Yes,
ma'am.
yeah, P inverse AP is just I. So because A is equal to I here. So here B is not equal to I. So A and B are not similar. This is a contradiction. Okay, fine. So again, the technique for finding P is given. Please go through this by yourself. Okay, let A be a 4x4 scalar matrix and B is similar to before this properties here. These are important again. Two matrices are similar, then the rank, trace, and determinant, all of them are same. But the converse is not true. That means if rank, trace, and determinant all are same, still it is possible that the matrices are not similar. The same example is still applicable. Here you see the trace, rank, and determinant all are same, but still the matrices are not similar. Okay, fine. Let A be a 4x4 scalar matrix and B is similar to A. What is the determinant of A? So a scalar matrix means how it looks like. A is equal to
Product of the
Alpha
diagonal elements
alpha
of
times
B.
of I, where alpha is some real number. Okay, and A and B are given to be similar. So what is the determinant of, here I wanted to ask, what is the determinant of B? What is the determinant of B?
Same
Alpha
as
power-
the
alpha power
determinant
4.
of A.
It is alpha power 4. Okay, can the determinant of B be negative here?
No, ma'am.
Okay, so suppose for example I am giving a matrix like this, maybe something like -1 2 3 4 0 1 1 1 0 0 0 or 0 0 1 2 0 0 0 1. So the question is, can A and B be similar?
No, ma'am, not.
How
B
can
has
you
to
say that?
be.
Different signs are there.
It has to be the same matrix.
Okay,
of
first of
A.
all, for a scalar matrix, it cannot be similar to any other matrix. Another thing is that here determinant of B is -1. Okay, either way you can say that. So A is not similar to any other matrix. Okay. So by the way, here the other observation is that if B and C A are similar, what is the other observation you have about A and B? What is the relation between A and B?
Same rank, same trace, same determinant.
They should be first of all equal, right?
Yes, ma'am.
Okay. Let A be an n by n matrix which represents an isomorphism between two n-dimensional spaces. It means what? If you have T from Rn to Rn, which is an isomorphism, and A is the matrix representation of T. Okay. Can A be similar to a matrix B whose nullity is greater than or equal to 1?
No, ma'am. Because the nullity of A is 0.
Yeah. So here you see that here nullity of, what is the nullity of A?
That is 0 because isomorphic.
Yeah, because of isomorphism, you have rank to be equal to n, and if rank is n, nullity is 0. Okay. So if nullity of A is 0, then you know that here rank of A is n, and so rank of this B should also be n. If rank of B is n, again you know that nullity should be 0. So this is not possible. Answer is no. So you see that the matrix cannot have nullity greater than or equal to 1. Is this clear?
Yes, ma'am.
Okay. Right. So this is something we have already seen. Quickly answer this. If A and B are similar, then A inverse and B inverse are similar. Is that true?
Yes, ma'am. True.
Okay. If A and B are similar, then A square and B square are similar.
Not necessarily.
Is it? It's true, right? Because in fact, A power K and B power K are similar. We have proved, right?
Ma'am, can you do that again? How?
We have already done this. B is equal to P inverse AP. So B square is equal to P inverse AP into P inverse AP. So you just have to switch brackets and you will get P inverse A
Yes,
square P. Same
Yes,
way you
ma'am.
can do for any power, right?
Okay.
If A square and B square are similar matrices, then A and B are similar. This part, is this true?
No, ma'am, it's not true.
No.
Yeah, so we saw that matrices examples like -1 0 0 1 and 1 0 0 1. So these two are A and B. A square are similar, but A and B are not similar, right? Incorrect. If A and B are similar, then their transposes are similar,
Yes, ma'am. True.
right? Okay. Okay, so the next topic here is affine subspaces and affine mapping. Regarding this, the main thing you should know is that corresponding to every affine subspace, there is a subspace. Okay, so before that, so you should first of all have a clear understanding about subspaces. So in general, I'll quickly ask you, what are all the subspaces of R2?
That is the 0 point only, and any line passing through origin, and the entire R2.
So for R2, the 0 subspace, line passing through origin, and R2
Entire
itself.
R2.
So these are all the possible subspaces. Now what about R3?
Just need to add plane passing through origin.
Line passing through origin and plane passing through origin, and then R3.
And R3 itself.
So what is the dimension of these spaces? So here dimension is
0.
Dimension is
1.
1 and dimension is
2.
Here also dimension 0.
0.
Dimension is 1. Here dimension is 2.
And 3.
Dimension is 3. Okay. Fine. So now affine subspaces are nothing but translations of subspaces. Okay. So suppose you are having U as a subspace, you just add another vector and that becomes a affine subspace. Okay. So you see that an affine subspace of a vector space V is a subset L such that there exists a V and a vector subspace U such that V plus U is equal to L. Remember, here this V is not unique, but this U is unique. Okay, V is not unique, but U is unique. Sorry, there is some issue today. I don't know. So here U is unique. This subspace U is unique. But V is not unique. In this representation, L is equal to V plus U. V is not unique, but U is unique. It means what? For the same L, you can have different V. Here, if you have V and V dash. But this U and U dash, they cannot be different. They are same. Okay? Fine. So remember that every subspace is also a affine subspace. Okay? Fine. And the dimension of affine subspace, suppose you are having L is equal. Sorry, what is going on here? Okay. Suppose you are having L is equal to V plus U, then dimension of L is nothing but dimension of U. Okay. So what are all the two-dimensional affine subspaces? So these are all the subspaces of R2 and the corresponding affine subspaces are just translation. So any point or any straight line or any, so the whole space R2. These are all the possible affine subspaces of dimension 2. And three-dimensional affine subspaces. So here you have the zero subspace, span of any single vector in R3 and span of any two vectors from R3 and the whole R3 itself. So these are the affine subspaces in 3 dimensions. Okay. Fine.
Yes, ma'am.
So addition and scalar multiplication, how we do in affine spaces. Suppose you are having two vectors in this affine set L. So then you see that L plus L dash, you don't do anything to this V. V will be fixed here for addition and scalar multiplication. Remember, the vector V is fixed. Because you already know that addition and scalar multiplication are already defined only for subspaces. So we are going to do the addition and scalar multiplication only for the elements from the subspace. We are not going to disturb this V at all. Okay. So remember that for addition and scalar multiplication. And how do you relate affine mapping to a linear transformation and a linear transformation to a affine mapping? Okay. So suppose you are having f from L to L dash be a function. Consider any V in L and the unique subspace. So L is equal to V plus U. Now f of V belongs to L dash. Okay. So now you can define affine mapping from L to L dash if this function g from U to U dash given by g of U is equal to f of V plus U minus f of V is a linear transformation. So just you have to remember this point. We have explained how this is a linear transformation already. Same way, so here what happens? Given a affine transformation, what is the corresponding linear transformation? Same way, if given a linear transformation, how do you get affine mapping? So affine mapping, you can get it in this way. So you know that f from L to L dash, L is V plus U. So here you see that this f of V plus U, if it is defined, so here V dash is the element in L dash. So it is V dash plus T of V. So this is how you are defining affine mapping. So from affine mapping to linear transformation and from linear transformation to affine mapping, these two you just remember. Okay. So the properties and all we have already discussed. I'll quickly do few problems here. Let L1 x comma y comma z is given by this and L2 is given by this. So I already have mentioned to you, suppose you are having any subspace like this. So what does this represent? What does this represent? Subspace
Of R3.
which is a plane passing through origin. Okay, subspace of dimension 2, plane passing through origin. And what is the corresponding affine subspace for this given subspace?
At the place of 0, you need to put some.
Yeah, at the place of 0, you will have some other constant.
Yes.
That's all. This is the corresponding affine subspace. So now L1 and L2 are given to be affine subspaces. So what are the corresponding subspaces? It is very easy to tell, right? What are they?
X plus y plus 2z equal to 0 and 2x plus y plus 2z equal to 0.
Yeah, x plus y plus 2z is equal to 0 and 2x plus y plus 2z is equal to 0.
0.
Okay, fine. Please be careful while answering such questions. In some cases, the same subspace, you see that it can be rewritten in a different way. Maybe here you will have something like, maybe instead of this condition, maybe you are given like 2z is equal to minus x minus y. So you don't get confused. You just have to be careful. So the same can be written in different ways. So please be careful while answering such questions. Okay.
Okay.
Consider the affine subspace L1 and L2. So this is an affine subspace and this is another affine subspace. W1 and W2 are the corresponding subspaces. So what is W1 first of all? Set of all x comma y comma z such that x plus y plus 2z is equal to
0.
0. So it means it is set of all x comma y comma minus x minus y by 2. Correct?
Yes, ma'am.
So instead of z, you have minus x minus y by 2. So here, so the basis element you will have is this 0, 1 minus 1 by 2. So if you are getting rid of the fractions, you will get 2, 0, minus 1, 0, 2, minus 1. So W1 is the span of these two vectors. Okay, here it is given span of 1, 0, 0, 0, 1, 0. So you have to just match whether these two subspaces are the same. Here you are getting the xy plane. So, sorry, this one, right? So this one is 1 minus 1, 0, 0, 1, 2. So do they look similar? Not in any way, right? So make sure this W1 is not equal to this. Definitely it does not look like this. First of all, whether this 1 minus 1, 0 belongs to this subspace or not?
No, ma'am, it's not.
It is there in the subspace, right? 1 minus 1 is 0 and 0, 1, 2. Only this element is not there in your W1, right? So this element is not there in W1. This is there in W1. So this cannot be the answer. What about W2? So W2 is the set of all x comma y comma. Here what is this? That should be
0.
0, right?
0.
X, Y in R. So straight away you can see that this is the correct option. Now what about option 3? W1 and W2 represent a line passing through origin in R3. Is that correct? What is the intersection of these two spaces?
Yes, ma'am, it is correct. The intersection is going to be x comma y comma 0.
Ma'am, z is equal to 0. That's why x plus y is equal to 0. That is line passing through the origin. X is equal to y.
Exactly. Okay, so you need to consider both the conditions. So W1 intersection W2 will give you set of all x comma y comma z such that z is equal to 0 and x plus y is equal to 0. So it means y is equal to minus x and z is 0, which is the line passing through origin in R3. Okay, so this is it. Is this clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Ma'am, in option number second,
Sorry?
for option number second,
Hmm.
we can say it is a plane passing through origin if not given the
It is a plane passing through.
origin. We can say.
We cannot say any plane passing through origin. Specifically, it is the xy plane.
Okay.
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 Only your z value is becoming 0 here.
Okay.
Is that clear?
Yes, ma'am.
Yeah. Okay. So dot product in Euclidean space, you know how to do dot product u dot v, coordinate wise dot product, and what is the length of a vector? What is the norm of the vector? Square root of u1 square plus u2 square plus etc.
Plus
un square. So you know how dot product and norm are related. So norm u is equal to square root of u dot u, which is given by this. Okay, fine. An angle between two vectors, theta equal to cos inverse of u dot v by square root of u dot u into square root of v dot v, which is norm u into norm v. The denominator is norm u into norm v. Okay, fine. So inner product spaces, you have these four conditions: positivity, and then you have this bilinearity property, and then you have the symmetric property. If all these conditions are satisfied, then it is called an inner product space. Such a function is called an inner product space. Okay, fine. And for norm, you have these three conditions: triangle inequality, and here norm cx is equal to mod c times norm x, and norm x greater equal to 0, and norm x equal to 0 if and only if x equal to 0. So how do you induce a norm from an inner product? By norm of v, you can induce inner product, use the inner product given by square root of inner product v comma v. Okay, so these are some basic things about dot product and inner product spaces. So I am quickly going through these things and going to do some problems here. Consider two vectors u and v. So they are said to be orthogonal if u dot v or inner product u comma v is equal to 0. Okay, so now from using this definition, it is given that a and b are orthogonal vectors. Okay, also a plus b and a minus b are orthogonal. Then which of these options are correct? So if a plus b and a minus b are orthogonal, what do you know? This is 0. It means inner product a comma a plus inner product b comma a plus or minus inner product b comma a comma b minus inner product b comma b is equal to 0. Now what is inner product a comma b given to be? What is inner product a comma b?
0.
It is 0. So now substituting this 2, you get inner product a comma a. So this is 0, this is 0. Minus inner product b comma b is 0. So it means they are equal. So if they are equal, what is this equal to? This is nothing but norm a square, norm b square. So which option is correct from here?
Second option.
Okay, these two are incorrect. So you know what is an orthogonal set of vectors? A given set of vectors is said to be orthogonal if they are mutually orthogonal to each other. Okay, take any pair, they should be orthogonal. Okay, and what is the important property about orthogonality? Orthogonality implies independence. This is a very important property. If you have a set of orthogonal vectors, then they are always linearly independent. Okay, and what is an orthogonal basis? A basis consisting of orthogonal vectors. That's all. Okay, fine. And orthonormal means norm of each vector should be 1. It is orthogonal set where norm of each vector is 1. Okay, and basis means again the norm of each vector in the orthonormal set, the orthogonal set is 1 for the basis. Okay. So here already I made this mistake in the notes also. How to obtain orthonormal set from an orthogonal set? You simply divide by the norms of those vectors. Then you will get the orthonormal set. Okay, fine. Okay, now look at this question. Suppose B, I have not yet started projection, but anyway, no problem. Suppose beta is an orthogonal basis of an inner product space. If there exists B in V such that B inner product B comma Vi is 0 for all I equal to 1 to n, then V is equal to 0. Is this true? Is this true? Yes or no?
Yes,
If
ma'am.
the- So you see, this is a basis, and an element is orthogonal to all the basis elements means, so the vector itself should be 0, right? So how do you prove that? Already we have discussed this. There are several ways to do that, because V is equal to alpha I times of Vi. So sigma alpha I Vi comma Vi, this inner product is 0, and you know that this is an orthogonal basis. So what is that you will get is that alpha is equal to 0 for all I, which means your V is equal to 0. Okay. There exists an orthonormal basis for Rn with the standard inner product. What is that orthonormal basis? E1, E2, En. Right? Okay. So PW represents the projection of the vector space of inner product space V onto a subspace W. What is the range of PW intersection null space of PW? If you remember, it's not if you remember, because you are approaching n term, you should know what is range of PW and null space of PW. What is the range and null space of the projection map? What is the range of PW? It is
W.
W. And null space of PW is the orthogonal complement. What is the intersection of W intersection W per?
0.
0.
Okay. Fine. 0, -1, 0, 1 cannot represent a matrix corresponding to some projection. What is the property for a projection? If P is a projection, then P squared is equal to
P itself.
Right? So here, what is P square? Suppose you consider this as P. What is the P square here?
One.
-1.
-2.
So this is not equal, right? Not
Not
equal to P. So here this cannot represent a projection. Okay. Fine.
Yes.
What are the importance of orthonormal basis? So suppose you are having an orthonormal basis, finding the coefficients for any given vector, it is very easy. The coefficients are nothing but Ci is equal to inner product V comma Vi. Okay, this will be very handy if you are doing some problems. So please remember this. Okay. Choose the set of correct statements. In an orthogonal set, the norms of all the vectors are equal. Is it correct? Yes or
No,
no?
ma'am. No, ma'am.
No, right? Because only for orthonormal set, you know they are equal. And in an orthogonal set, the vectors are linearly independent.
Yes.
True. If the columns of an n by n coefficient matrix A comprises the individual vectors of an orthogonal set, then there must be a unique solution to the system Ax is equal to B.
Yes, it is true.
Yes. Because if the vectors are orthogonal, the columns are orthogonal, then you know that the orthogonal set is also linearly independent. So a matrix consisting of linearly independent column will have a unique solution. Right? Okay. So again, this is incorrect. The determinant of a square matrix formed by a set of orthogonal vectors in Rn is 0. True or false?
False.
A set of n vectors can never form an orthogonal basis in Rn minus 1.
Yes, ma'am.
True.
True.
True, right? So why this determinant cannot be 0? For a square matrix formed by orthogonal set of vectors, what happens?
Ma'am, all the element of the row are independent. That's
Yeah.
they are.
So all are linear independent means the determinant should be non-zero.
Yes, ma'am.
Okay.
And ma'am, for option number 7.
Option?
Last option.
Yeah.
What is the
So what happens to Rn minus 1? So suppose you are having n vectors in orthogonal basis, then what is the dimension of that? Suppose let us say v1, v2, vn. This is your orthogonal basis, let us say. So what is the dimension of the space corresponding to it? Dimension should be equal to, you have n vectors in the basis. So what is the dimension?
N, ma'am.
But here it is Rn minus 1.
Yes,
so it is incorrect. Oh, sorry, I put correct. Yeah. Can never form. Oh, it is given never form. So it is correct only, right? Yeah. Can never form an orthogonal basis in Rn minus 1. So it should be n. So it cannot form a basis in Rn minus 1. Correct?
Correct. Okay.
Yeah. Which of the following option is true? Let A and B be orthogonal matrices of order 3. Then A and B are equivalent matrices. True or false? What do you know about the determinant of A and determinant of B?
Not equal to 0.
Both are non-zero. So it means rank of A is equal to rank of B is equal to?
Yes, ma'am.
3.
3. So if the ranks are same, you know the matrices are equivalent. Right? Let A and B be orthogonal matrices. Then A and B are similar. Is that true?
No, ma'am.
No necessity.
Yes or no?
No.
No, right? It is not necessary. Maybe there are some examples. I have not given it here. Let's see. I can add it before uploading. Okay. Let A be a rotation matrix corresponding to the anti-clockwise rotation of the xy plane about the z-axis with angle theta. Then nullity of the matrix A is 0. Is that correct? Any rotation matrix, whether
Yes,
it
ma'am, it
is
is
xy
correct.
plane or any other thing, you know that it is a matrix corresponding to orthogonal transformation, right?
Yes, ma'am.
So if it is corresponding to an orthogonal transformation, so it should have determinant non-zero. So the nullity should be 0. Okay. A be a rotation matrix corresponding to the anti-clockwise rotation. Okay. And B be the rotation matrix corresponding to another rotation. Then A and B are equivalent matrices. Since both are rotation matrices, you know they are orthogonal matrices. So their determinants are non-zero. So again, using the similar argument, A and B are equivalent. True or false?
True.
Okay. Fine. So next, projections using inner product. So what is the projection of a vector B onto A? Projection of B onto A. This is the formula. Inner product A comma B by inner product A comma A into A. Okay. So projection of a vector onto a subspace. So this is a vector on a vector. And for projection onto a subspace, you need to first of all have an orthonormal basis. And then you can find the projection using this formula here. Okay. So irrespective of whatever choice of orthonormal basis you are going to get, you will still have the same projection. Okay. So now consider an orthogonal basis 1, 2, 1, minus 2, 0, 2 of a subspace W of the inner product space R3 with respect to dot product. If Y is equal to 1, 2, 3 in R3, then find projection of W in Y. Can you tell me what are the steps to find this projection? What is the first step to do?
We need to find an orthonormal basis for
So how do you
subspace
find the orthonormal basis here?
by Gram-Schmidt process.
By Gram-Schmidt process. Okay. So how do you do that? How do you do that? Gram-Schmidt. So you just have to remember the formula here. This, where is that? I skipped Gram-Schmidt or what? I cannot skip that, right? Oh, I gave it here. Please remember, you have to do this Gram-Schmidt process. So maybe let this be a practice exercise. I cannot take too much time for doing Gram-Schmidt here. By the way, are they already orthogonal? In this example, are they already orthogonal?
Yes, yes,
V1
yes,
and V2.
ma'am.
So in that case, it is not, Gram-Schmidt is not required,
Yes,
right?
ma'am. We can just
So
divide
V1
it by
inner
norm.
product V2, it is already 0. So you just have to divide by their norms. What is V1 by norm V1?
By √6.
Root 6. And V2 by norm V2?
Divided by 2 √2.
So you have minus 202 square root of 2 plus 4, 8. So 8 I can again write as 2 √2. So minus 101 by √2. Okay, fine. So you have the orthogonal, orthonormal basis now. So what is the projection formula here? This is the projection formula. So you need to do summation I is equal to 1 to 2 here, inner product V comma Vi into Vi. Correct? Yeah. So here instead of Vi, you are having Ui. So projection of Y here is inner product Y comma U1 into U1 plus inner product Y comma U2 into U2. Please do this computation yourself. Shall I leave this computation to you? You can do this inner
Yes, ma'am.
product computations, right?
Yes.
Oh. Okay, projection as a linear transformation. So you know that T from V to V can be defined using this projection. So this will give you a linear transformation. And what is the range of T? For a projection map, what will be the range? Remember,
Range is
always for
W.
projection map, it is always W. So what will be the rank?
Dimension of W.
And what is the kernel? Nullity is this. So kernel is simply W per, which is nothing but the orthogonal complement, right? So set of all V such that inner product V comma W is equal to 0 for all elements in W. So what are the important properties? P square W is equal to PW and PW of V is less than or equal to norm V. So the projection of a vector cannot be longer than the vector itself. Okay. So let V be the plane spanned by the vectors V1 and V2. Find V per. How do you do that? A comma B comma C. Let us say this is in your W curve. So before this here, you need to know this important property. Dimension of W plus dimension of W curve should be equal to dimension of V. Okay. So here you see that. So you are having W is equal to span of V1, V2. Okay. W is a subspace of R3 here. So this is, let us say, W per. So what should be the dimension of W per? From this, yeah. What is the dimension of W per here? You don't know what is dimension of W at least?
2, ma'am.
2. If dimension of W is 2, and what is dimension of V here? V is R3.
Okay, then it is 1.
1. So here in this for W-perp, you just need to find one vector in the basis. So let A, B, C belong to V-perp. So A, B, C dot 1, 1, 0 is equal to 0. A, B, C dot 0, 1, 1 is 0. So it means A plus B is equal to 0 and B plus C is equal to 0. So A is minus B and C is minus B. So what is your W-perp then?
Span of -1, 0, -1, or 1,
Minus
0,
1, comma 1,
1,
comma
-1.
minus 1. Okay, you know how to find now, right? Okay,
Yes.
let this be the standard inner product on R2. Okay, now W1 is this space and W2 is this space. Now what is W1-perp? How do you identify? So let's say A comma B dot X comma 2X is equal to 0. It means 2AX plus 2BX, sorry, AX plus 2BX is equal to 0. So A plus 2B times X is equal to 0. So what is this? A is equal to minus 2B. So what is your W1-perp? Can you tell? A is equal to minus 2B, or you can say 2B is equal to minus A. What is your W1-perp? Option
C.
3. Right? Okay. Now what is W2-perp? This is for W1-perp. What is for W2-perp? Set for A comma B orthogonal to X comma minus X minus 2X. So here you will have A minus 2B times of X is equal to 0. So it means A is equal to 2B. So what is W2-perp then? Okay. Do you understand how we are finding the orthogonal complement? Is this clear?
Yes, ma'am.
Can you please be louder?
Yes, ma'am. Yes.
Okay.
Yes, ma'am, it is clear.
Okay, fine. Okay. So consider a linear transformation. We are almost at the end. Consider a linear transformation T from Rn to Rn such that TV1 is equal to W1 and TV2 equal to W2. If W1 and W2 are linearly independent, then V1 and V2 are linearly independent. Is that true? Not necessarily, right? Yes or no? What is the answer
This
for
is like an on-to case, ma'am. For every V in V, let be defined a W in W. So if W is linear independent, then V should also be linear independent, right?
It should be, ma'am. I mean, the option is right.
Okay, so if it is right, please explain how it is correct.
Ma'am, linear transformation T of V1 is equal to 2 and W1 and W2 are linearly independent, then
Yeah, so you have to use the definition of linear independence. So here you have, so for option 1, so given that W1 and W2 are independent, it means, so you know that if you have any linear combination CW1 plus CW2 equal to 0, C2W2, then you should have C1 equal to C2 equal to 0. From this, let us see whether we are able to get this. So you are assuming that alpha V1 plus alpha 1 V1 plus alpha 2 V2 is equal to 0. You want to prove whether alpha 1 and alpha 2 equal to 0. So you simply take the transformation on both sides. So T V1 equal to 0. So alpha 1 W1 plus alpha 2 W2. This is V2 is 0. So from this information, we know that alpha 1 and alpha 2 are 0. So V1 and V2 are linearly independent. This is true. All right. Clear? Okay. So consider a linear transformation T from Rn to Rm here remember Rn to Rm such that Tv1 equal to W1 and Tv2 equal to W2. If W1 and W2 are orthogonal, then V1 and V2 are orthogonal. Is it necessary? Is it necessary?
No, ma'am.
No, right? So you can give several examples for this. So here maybe let us say T of 1, 1 is equal to 1, 0 and T of 2, 1 is 0, 1. So this is your V1, V2, W1, W2. W1 and W2 are orthogonal, but V1 and V2 are not orthogonal. Okay? So
Yes,
this
ma'am.
is correct. So this is for option 2. Let U and B be two vectors on an inner product space V. If U plus B and U minus B are orthogonal, we have already seen this option in the beginning.
Yes.
That is true. Let A be an n by n matrix, then the null space of A is the orthogonal complement of the row space of A. When both are viewed as subspaces of Rn with the usual inner product. So here some information is missing, right? Is it just true without U and B being orthogonal? Yeah, it is true. In fact, here you don't need this condition. Because what we have proved earlier, we assume that they are both 0. Right? Where was that question? Yeah. So here both are 0. So what happens if they are not orthogonal? Inner product A comma B is same as inner product B comma A. So this
Yes.
and this will get cancelled. So anyway, this option will be true. Okay? Fine.
Yes, ma'am. Yes.
Okay, so option 4, the null space is the orthogonal complement of the row space. This is true. Okay, always remember null space of A is the orthogonal complement of row space. This is a very important property. Okay.
How it is? I mean,
Can you explain
yes,
a little more, ma'am, if possible?
Okay, so here you want to. Sorry, something is happening here. Okay, so let us say. Sorry, something is again happening. Just give me a minute.
Ma'am, say before all.
Okay. Is the screen visible?
Yes, ma'am.
Yes, ma'am.
Okay. So let us say you are having x's in the null space of A. Okay, it means what? Ax is equal to 0. So
Yes.
now A is, let us say you are having R1, R2 up to Rn, n by n matrix. Okay, so now Ax can be write it as R1 dot x, R2 dot x, Rn dot x. Yes or no?
Yes, ma'am.
So now this is equal to 0. Okay, so now it means what? What is your row space, by the way? Row space is the span of R1, R2, Rn, right?
yes, ma'am.
So your row space is the span of R1, R2, Rn. Now you see x belongs to null space of A implies x belongs to the row space complement, right? Because it is orthogonal to each vector in the basis, so it is there in the orthogonal complement of row space. Do you agree? Yes or no?
Yes, ma'am.
Okay, the same using the similar argument. If x belongs to row space complement, then you have R1x dot R2x, all these are 0. So it belongs to null space. So do you understand this proof? How is this happening?
Okay, ma'am.
Okay.
That means
Or should-
row space of complement means the inner product has to be 0, right? With x.
Yeah, that is what is happening. Here, inner product is Ax is equal to 0. So R1 dot x, R2 dot x, Rn dot x, all are 0, right? Ax is 0.
Yes. Yes, ma'am. Yes, ma'am. Got it.
Okay, got it?
Yes.
Okay, fine. Okay, consider V is equal to R3 with inner product as dot product, and W is equal to X is equal to Y and Z is equal to 0. Let PW from V to W be a projection on W. Answer the following questions. Find the dimension of image space PW. What is the dimension of image space of PW? It's simply dimension of
W.
And what is the dimension of W? W is nothing but set of all x comma
It
x
is
comma
1
0.
only. Yes, ma'am.
Yeah, so it is 1. And what is the dimension of null space of PW? Null space of PW is nothing but W perp. What is the property I told you about this dimensions of W and W perp?
It has to be 3 minus 1, which is 2.
Yes.
So it should be 2, right? So this answer is 2. If V belongs to W is such that norm V is equal to 3, then find norm of PWV. So what happens? P of W is simply W. It means what? For any V in W, what is PV?
That is B only.
It is B only. So PWV is equal to, so it is same as norm V, which is again
that is 3.
Okay. Let A be the matrix representation of PW with respect to some orthonormal basis beta and gamma for V and W respectively. Then find the dimension of the null space of A square. So what do you know about PW square?
PW.
It's PW. So A squared will be same as
A.
A. So the null space of A is equal to, already we have found, right? Null space of
It is 2.
Yeah, it is 2. Answer is 2. You understand why it is 2?
Yes, ma'am.
Yes. Okay. So the answer here is 2. Because this is the dimension of W perp. Okay. Is this clear for everyone?
Yes, ma'am.
Okay, fine. So the Gram-Schmidt process, it is just a formula. So I'm not going to explain anything here. Please go through the formula. So the last topic here is that orthogonal transformations. So orthogonal transformation means inner product TB comma TW is equal to inner product V comma W. So any transformation satisfying this property is called a orthogonal transformation. It preserves inner product. So if it preserves inner product, it is going to preserve length and angles. So what does it mean by it preserves length and angle? Norm TV should be equal to norm V if T is a orthogonal transformation. And suppose V and W, the angle between V and W is theta. What is the angle between TV and TW?
Theta.
Again, theta. That is the meaning of preserving length and angles. Okay, fine. And what are orthogonal matrices? Orthogonal matrix is a matrix which is a matrix corresponding to an orthogonal linear transformation. It satisfies this property. Okay. So any matrix satisfying this property is called a orthogonal matrix. Remember, A transpose is equal to I means rows of A are orthonormal and columns are orthonormal if A transpose A is equal to I. Okay, remember this. Okay, so the very last problem of this session, let A be a 3 by 3 orthogonal matrix. Which of the following options are true? The rows of A form a basis for R3. Is that true?
Yes, ma'am. It is true.
Yeah. What about the columns?
True.
True, ma'am.
That will also form a basis. The columns of A form an orthogonal set of vectors of the inner product space R3 with respect to dot product. Is it true again?
Yes, sir.
Yeah.
Yes.
What is the rank of such matrix?
3. That is 3, ma'am.
Yeah, determinant. What about the determinant? We have already discussed. Let me come back. It is
Equal to
non-zero, we
0.
know. Rank
That is
of A is equal to
3.
3 here. It is incorrect. The system of linear equation Ax is equal to B. Since the determinant is non-zero, what do you know about this system?
Unique solution.
It will have a unique solution. So this answer is incorrect. By the way, what about the determinant of an orthogonal matrix? So you know that A transpose A is equal to identity. So from the property of determinants, determinant of A transpose A is equal to determinant of identity. What is the determinant of identity?
1.
1. So determinant of A transpose into A is determinant of A transpose into determinant of A, which is 1.
1 or minus 1.
Yeah. Determinant of A whole square is equal to 1. So determinant of A is plus or minus 1.
Yes,
Okay,
ma'am.
so this
Ma'am,
is a
here in this question, the columns of A also form an orthonormal set of vectors of the inner product space R3, right?
orthonormal basis, in fact.
Okay.
Okay.
Because all the vectors, all the vectors with respect to the rows are orthonormal, right?
Yeah, yeah.
Okay.
Rows also will form, or rows are also orthonormal, columns are also orthonormal. That is a definition for us, right?
Okay.
So the rows are orthonormal as well as the columns are orthonormal.
Okay, for if the rows and columns are not orthonormal but orthogonal, is there any relation?
In that case, it will be a scalar matrix, not a scalar matrix. It will be a diagonal matrix.
Okay, ma'am.
Okay.
Okay, ma'am.
Fine.
So it will not be called as orthogonal matrix, right?
No, it is not an orthogonal matrix. No.
Okay, ma'am.
Okay, so we are done with the revision of week 5 to 8. I hope this session was clear to everyone, and I hope it will be useful for you.
Yes, ma'am.
So in the next session, we will do the revision for week 9 to 11. Okay, please.
Ma'am, what about the notes?
Yeah.
The notes.
Yeah, I will upload. So
what
please
is
revise some topics before coming so that it is easier for you to understand. Okay.
Okay, ma'am. What is the week-wise weightage of for interim?
What is